So welcome to this second part of this session. I am Chiara Casotto. I am a former student of the ROSE School. So the last time, I'm also very excited because the last time I was here, it was for my PhD defense. And I was pregnant of my first daughter. And now I'm pregnant of my third one. So please don't invite me anymore on this stage. I think I've done enough. So I now work in Studio Calvi, so with seismic assessment, retrofitting, design. I'm very happy to be part of this team and to be part of this community. I had prepared a small introduction, but after what I have seen, these very great works, I can just say that I am overwhelmed, and there is not too much about theoretical speak about the relationship between researcher and professional life, because we have seen that it exists and it is fruitful and it is the way we should go. So I am just starting. The first presentation is by Paolo Morandi. I think you all know him. So he's senior researcher at the Eucentre, and his presentation is about wait a second, seismic verification of masonry infills, and so on.
Thank you for the nice introduction. Good morning, everyone. I'm really pleased to have the opportunity to talk in front of many alumni, friends, and colleagues. Here in Pavia from more than 20 years. I got my PhD a few years ago. I used to work as a postdoctoral researcher, and then since 2017 I entered at the Eucentre as a researcher. And the funny thing is, this friend of mine said, why you are still there? You had so many opportunities, maybe more convenient opportunities. And my answer is very simple. I enjoy. I enjoy the environment, I enjoy the research, I enjoy the topics, I enjoy the friends and the colleagues in Pavia. For me, really, this became a real second family. So, I'm not good in saying this stuff. I prefer to talk about my research topics. So, in my presentation, I would like to show you some of the research that we conducted on the seismic verification of masonry infills in the last, let's say, 10 to 15 years, but try to translate it into indication for professionals. I don't want to spend too much time regarding the effects of earthquakes on infills. We saw a lot of examples of collapse, in-plane collapse, out-of-plane collapse of masonry infills. We also are well aware that there is an interaction between in-plane action and out-of-plane action due to the simultaneous action of the seismic action. So we found out-of-plane seismic action, which is usually greater at the upper floor, but damage usually was observed lower than the intermediate floor, where the interstory drift demand is higher. So we know very well that, and we found also in these pictures, that many of the collapse and the damage, of course, at the intermediate floors, due to this interaction between in-plane and out-of-plane action. So remember that, because we need to know that for the safety verification of the infills. Which are the aims of seismic verification? The aim is to limit the in-plane drift, so limit the damage, which is correlated to the drift, of course, and guarantee sufficient out-of-plane stability. The first aspect was pretty well known. This second, maybe not. I above all in the last 2-3 years, I saw a lot of presentation and papers saying, infills are very vulnerable to seismic action, we know that. So vulnerable, are reinforced masonry very, very vulnerable. But sometimes I'm seeing pictures like that, where according to the estimated PGA, which is pretty low, about 0.2 G, there is complete destruction not only of the infills, but only of the structure with soft story. This is clearly without any design, seismic design of the structure and of the infill. But on the other side, we also found a lot of situations which are reinforced concrete with infills, masonry infills, without damage, or with really little amount of damage. Usually in buildings which are mid-rise, 3 up to 4 stories, recently constructed, so probably following the recent modern codes, but, however, subjected to pretty high level of PGA, of seismic intensity. So which were the lessons learned from post-earthquake surveys? First of all, as I mentioned before, the interaction between in-plane and out-of-plane, but then also, according to me, that some causes of vulnerability of the infills are not only due to the intrinsic vulnerability of the masonry, but also to poor or complete lack of seismic design and of the structure and of the infills, and also poor construction quality. And then, question mark, are the recent buildings so designed with, according to modern seismic norms, usually low-rise reinforced concrete buildings, perform satisfactorily? Probably yes, but we are still working on it. Also, with the aid of a group of Maria Rota, we are working on the derivation of empirical fragility curves, looking really to more modern buildings with masonry infills. This is from the earthquake, but from the experimental evidence, what is the experience that we got in the last years? It's a normal procedure when we want to test infills is to first test in plane with pseudostatic in plane test to increasing level of drifts, followed by out of plane test, usually conducted in quasi-static manner. So the story says that one of the first of this type of test was conducted in US mid-90s. Then Michele, Calvi, and Davide Bolognini in 2001 made a milestone, I would say, a very important research following this type of approach, and then a little bit of silence. After the 2009 earthquake, Aquila earthquake, there was still a speed up of this type of test. And many tests were conducted in this way in the last 15 years. The objective of this is to try to evaluate an interaction, a relationship between in-plane drift and out-of-plane strength and also out-of-plane resistance. What is missing is probably the dynamic component, in particular the out-of-plane dynamic components. So 5 years ago, we started with a project between Eucentre and the Italian Department of Civil Protection, a huge experimental campaign, where the in-plane tests were conducted in pseudostatic manner, but out-of-plane tests on shaking table, so dynamical. We conducted up to now 19 frames, tested so far, with different boundary conditions, different thickness, with and without openings. The masonry that we are working with is, let's say, weak masonry, so in this case, with clay units with perforation, horizontal perforation. And these are some of the examples that were shown and discussed broadly yesterday by my 3 curricula here. This was important not only for the evaluation of the capacity, but also mainly for the evaluation of out-of-plane demand. So, resuming, weak masonry infills have significant in-plane damage starting from low level of drifts, and there is a strong reduction of out-of-plane strength when in-plane damage level increases. But another thing that we have found, that in case that all edges are bounded, large out-of-plane stability is guaranteed when the in-plane damage is limited, even on weak infills. On the other side, robust, thicker, and stronger masonry infills, of course, provided a reduced in-plane damage compared to weak solution, a high stability against out-of-plane actions, but the problem is the local effects, so the thrust of the infills on the reinforced concrete elements. So the question is it really possible to design and build safe masonry infills in seismic areas? According to me, yes. And this is possible because various solutions are in the market and depends on the seismic hazard that we are dealing with. So we can do single leaf robust reinforced masonry infills bonded to the structural frame up to, let's say, moderate seismic hazard. But then when we are moving to high or very high seismic hazard, we can handle innovative or reinforced solutions. But in any case, we need to correctly apply the modern seismic codes. And above all, starting from adequate structural design of the structure. So, for example, dual or wall structure, of course, are much better than resisting concrete moment frames. Different masonry topology, what we call traditional or reinforced masonry topologies, are defined in the new Eurocode, the new draft of Eurocode, as interacting non-ductile. And this is simply a reinforced masonry which is put after the hardening of the reinforced concrete frames in perfect contact with the frame, without any gaps. There are then reinforced infills, which could be reinforced in the bed joints, vertical reinforcement, or reinforced plaster with steel or composite mesh, which tends to increase, of course, the in-plane out-of-plane resistance, and in some cases also the in-plane ductility. But what I would like to focus a little bit more in detail is these interacting ductile infills. Ductile infills are dot infills where, in principle, you are subdividing the panel in 3 or 4 sub-panels, separated each other by sliding joints or deformable joints, and with some soft material at the interface between masonry and concrete. In Pavia, we developed a system like that, with sliding joint composed by plastic elements as sliding that reached 3% of drift, as you can see here, so about 10 centimeters of horizontal displacement, without really big damage. The damage that you see is only concentrated in the corner of the sub-panels and mainly concentrated in the plaster. So, big level of ductility, high level of ductility, and a lot of energy dissipation. I would like also to say 2 words regarding the non-interacting infills. This is interesting. According to the new draft of Eurocode 8, interacting infills are no in-plane interaction, so no safety verification in plane. Theoretically, you should get a gap between the masonry and the frame, vertical and horizontal gap. But warning, some issues. First of all, out-of-plane restraints. We have to design it. Second, what occurs if the seismic action is larger than the action assumed in the design? There is pounding, there is impact. Third, does it exist a magic material which is softer, very soft, but at the same time that comply with acoustic, thermal, and fire requirement? Can be really non-interacting? So there are cases which are defined as decoupling, but to me, these remain still a theoretical solution. The solution that has been proposed can work, and work well also, but should be considered as interacting, because there is an actual interaction between the frame and the infill, and this must be considered. After this long introduction, I would like to get into some of the seismic design approach of the infilled reinforced concrete beam in Europe. We all know, I'm talking about only linear analysis, no? Analysis for practitioners, not for researchers. First of all, we need to do linear analysis with a seismic action, design response spectrum using Q factor, equivalent static or multimodal analysis with response spectrum. We know well that. And we have 2 types of verification. A drift verification is usually conducted at serviceability limit states, and an ultimate state condition where you had to verify what? The structural resistance of the elements, the out-of-plane verification of the infill, but also, and this is new in the new Eurocode, the verification in drift, in plane drift, also at ultimate conditions. So I would like to discuss a little bit about that. So we had to verify, first of all, that the displacement demand would be less than displacement capacity at different limit states. This is simple, easy. But how can we deal with drift demand? How can we compute it? All of us, when you design a concrete frame, or almost all of us, consider the masonry infills only in terms of masses and vertical loads, without stiffening effects, right? And this is still possible in the norms and also in the Eurocode 8. But this is, of course, a conservative approach, above all in the case where the interacting infills are regularly distributed. Of course, you are overestimating the drift demand. So a few years ago, we defined a method, a very simplified method, where starting from the results of calculating the drift on a bare frame, we account a posteriori for the stiffening and the strength contribution of the infills through, let's say, a magic coefficient, very simple to be computed, is Cj, which is a ratio between the contribution in stiffness in plane of the infills and the contribution of the structures. This is very simple to be computed, like a simple spreadsheet. So what we do, we can get into this relationship with the drift of the bare frame, and according to this Cj, we can compute the corresponding drift of the infill frame. And the Cj, of course, depends on what? It increases at the increases of the stiffness and the strength of the infills, or when the decrease of the structural stiffness. But could be also close to zero when you have, for example, very strong, very stiff structures like wall or jewel structures. So that means that the drift on the bare frame is equal to the drift of the infill frame because there is no contribution or stiffening effects of the infills. And this was validated by hundreds of nonlinear dynamic analysis on different building configurations. This was appreciated by the committee of Eurocode 8. In fact, it was included in the informative annex of the new EC8. But this last method opened a possibility of optimize a little bit the design process. Because you can play not only with the structural dimensions, columns, beams, walls, but only with the infills, which are interacting. So we can really have an optimization of it to try to reduce what? The in-plane demand, the drift demand of in-plane. Because this is very important, not only for the verification, in-plane verification, but also, we will see in a minute, for the verification, for the out-of-plane verification of the infills. So this is open new strategy of design of infilled structures. Few things regarding people that say, okay, I'm doing linear analysis. Now why you do that? Put a simple struct, diagonal struct, which represents the stiffness of the infill. Yes, but my question is, which stiffness should I use? The initial one, a second one, and then which stiffness I have to calculate at operational limit state, damage limit state, ultimate limit state. And then remember, at the ultimate limit state, so severe damage, for example, I always have to carry out an analysis on the bare frame because we cannot guarantee the complete interaction at the ultimate conditions between infill and frame. So this is remain an open question. Capacity of drift. What we did? Eurocode said, tell me the drift limits at different infill topology and different limit states. So we start to collect a lot of tests, in-plane tests. We collect 175 non-ductile infills, 15 ductile infills. For all of them, we define different metrics of damage, operational, damage limit state, life safety, and collapse. And then we was careful in doing that. So not too small specimens. So we decide to use minimum height, minimum dimensional specimen because we are aware the smaller specimen tends to increase displacement capacity due to confinement effects. This is for structural walls, but we use the same approach also for infills, which needs to be verified. So we did some statistical processing of it, differentiating between different masonry topology, and we end up with this table, which is included in the Eurocode, the new draft of Eurocode. Is still finished the work? No, I wouldn't say that. Additional tests are needed. Some typology are not representative in this data set. Second, reducing, so in keeping only the bigger samples, we reduce a lot the numbers of the samples. And third, what is the drifted severe damage? The mean divided by a gamma, and we did something like that. We compute the mean divided by a gamma about 1.2, 1.25. But this is not the correct approach. There is here Junio that knows very well that, so we have to work a little bit more on that in the next future. Remember, I don't have time to get through details of this, but remember only that also the trust of the infills against the reinforced concrete frame is an important issue. You have to take into account the moment distribution and shear distribution changes as respect to bare frame situation. So the norms considers that, and please remember to consider properly that, above all in the case of robust masonry infills. But I'd like to only give you a few other messages regarding the out-of-plane verification, particularly starting from seismic demand. So, to compute seismic demand, we know that this is just the product between the out-of-plane normalized acceleration times the total weight of the infill divided by a behavior factor. And usually this force is distributed uniformly, just dividing by the frontal area, uniform distribution. How many expressions are in the course now to the evaluation of SA? Too many. QA, codes say take 2. Fine for robust infills. Too optimistic to me for weak infills. You should reduce 1.3, 1.5, research is needed. And it's really always uniform distribution of forces. So here are some of the expressions that you know very well. I would like just to show you a very rough calculation, 5 minutes to do that, but only to get an idea. We perform test, out-of-plane test, deriving artificial oscillograms against a reference response spectrum with pretty wide range of frequency in order that the frequency, natural frequency of the infills get into this frame. So there is sort of resonance. Let's say TA equal to 1 is equal to 1, let's say. Let's assume that. It's not exactly true, but okay. And look the results of the dynamic out-of-plane test. The ratio between the maximum acceleration at the center and the acceleration, peak acceleration at the base is about 5 times, which makes sense. But look at the results of the expression, considering the critical damping equal to 2%, which is the one assumed by the norm, by Eurocode 8. There are very big variation of it. So I'm really strongly saying that we need to define one expression which is suitable for masonry infills, which is not present right now. And we can use, for example, results of shaking table test, dynamic test, because we are one of the first situations that we have the possibility to work with to derive solid expression for the evaluation of out-of-plane acceleration. The second aspect that I would like to underline is this. When the structure is, the infill is bounded on all the cases like this, you know, for sites, there is actually a triangular, almost triangular distribution of acceleration, and of course of forces. But remember that we are assuming maximum acceleration in the design approach times total mass. So it's like to assume a uniform distribution of load. We are overestimating the force of about 2 times and the moments of about 1.5 times. Okay, this is only, we cannot generalize that, okay? It can be seen only in this condition. If different boundary condition occurs, of course, different distribution of the forces. Displacement shaped forces are also possible. So, but this is to bear in mind for when you do codes. And this is the last thing that I would like to discuss. It's interesting one, is I think nice, because we try to evaluate the autoplane frequency through, I don't know, but smartphone. How? We punched with a hammer 3 times. This was an idea about people with the car, you know, people loves music and sound, so it really helps a lot in doing that, but we are developing that. We are hammering 3 times the wall. We are there with the smartphone, 20 centimeters of distance. And we are acquiring sound waves on our smartphone. And our smartphone has also the converter between analog to digital. And with the digitalized sound signals, through MATLAB, simply, we calculate the frequency through fast Fourier transforms. Very easy. So this is possible when the frequency of your wall is higher than 20 Hertz, because below 20 Hertz you need a microphone, but the situation is the same. Look at the results. The frequency calculated in this way is incredibly similar to the frequency that we have evaluated from accelerometers, both with hammer test and with simple white noise test. Unbelievable. This opened really a huge possibility for acceptance criteria on new infills, but also to verify existing ones. You can compute the frequency. In principle, you can also compute, evaluate the boundary condition of the infills, which is very important. It's very, very important, above all for autoplane verifications. And then you can do that at cost almost 0 and very quickly. In 1 hour, few seconds, you can get the results of each wall. So this is really probably future possibility that could be exploited in the future. I would just to finalize this, remembering that for the autoplane capacity, what is the safety check procedure? First of all, you have to evaluate the autoplane seismic demand, okay? Secondly, you have to evaluate the autoplane resistance of the undamaged panel, for example, with the arching mechanism. But then you have to consider the first aspect that I mentioned, so the interaction between in-plane and out-of-plane. So we developed some expressions, here are some of them, in which you can get into the in-plane drift at severe damage, at ultimate mistake, in order to get the reduction factor that you have to use to multiply the autoplane resistance of the undamaged panel. This is, of course, very important. Test dash lines represented pseudostatic test. The red one, the dynamic test. Of course, dynamic tests are less conservative than pseudostatic. This is usual. And black one are the line of the Eurocodate. So even more conservative of the actual result correctly, according to me. And so you have multiplied this beta R, this coefficient, the reduction coefficient times the undamaged panel, the resistance of the undamaged panel, and then of course make safety checks. Lastly, within RELUIS, UniPV, University of Pavia, Eucentre, together with University of Naples and other 5 research units, developed after 10 years of work this document, which is guidelines for seismic verification and design of masonry infills in false concrete structures, which will be soon publicated with RELUIS. So this would be really important document, because one of the first documents which talk about seismic verification of masonry infills, not only in Italy, I think, at least in Europe. I would like to finalize my presentation saying these things. It's really difficult to translate the numerical and experimental results into simplified procedure or codified procedure. It's very difficult, because you have to be conservative enough, but not too conservative. Because if you are too conservative, you risk to push the market towards solution, towards some solution, and this is not true. I make an example. If you underestimated too much the performance of our reinforced masonry infills, you are pushing the market towards innovative solutions, which are fine for larger, high values of hazard, seismic hazard. Okay? But maybe this is too much. So what I'm saying, it's really difficult to balance between conservativeness and effective results, according to results of the research. So many areas of further investigation on innovative solution, in plane verification, out of plane verification. I told you that. We are plenty of nice projects at Eucentre at the University of Pavia regarding infills, experimental and numerical ones. So I really enjoy if someone wants to talk with me, with Guido, to discuss a possible collaboration, students, colleagues, researchers, because really we have work for the next years. So I would like really finally thank Professor Guido Magenes and my former PhD students, Sagnac, Ricardo Milanesi, who's here, Andrea Rossi, my tricuru Guasuria, she got her PhD yesterday, congratulations, and also my colleagues at Eucentre, Luca Albanesi, Carlo Manzini, Davide Bolognini, and Filippo Da Caro, and many others. Thank you very much for your attention.
Thank you, Paolo. It was very, very interesting, very clear also for practitioners and useful. So we are looking for I'm looking for the guidelines to be ready.
Hopefully in the next weeks, months, weeks, I don't know. They will be there. Yes, they are finalized.
And now it's a time for questions from the audience. Yes, Professor Calvi.
Sì. Thank you, Paolo, for your presentation. Very interesting. Just a small curiosity. When you are saying that we are overestimating of 2 times the acceleration because we are multiplying the entire mass times triangular shape, I have 2 doubts. One is that the triangular shape, according to your drawing, is not only in the horizontal direction, it's also in the vertical direction. Therefore, it's at least 4 times, it's not 2 times, it's much more.
Yeah, in the case of...
This is one. But the other consideration is in the opposite direction. The acceleration at the floor, at the tip, and the 2 sides is not 0. So you mean that you are overestimating it because you are summing to the amplification of the frame of the infill itself, the floor acceleration that you are using instead of 0 at the sides, or the 2 effects are compensating?
No, I explain better because this is a very interesting question. When the maximum force occurs, we had that type of profile here. Okay, this is the time where I have the maximum force, the peak force. So maximum acceleration in the center of the panel, and small, not 0, but smaller, much smaller values of acceleration at the edges, at the base, the floor, let's say. Okay, when you got maximum acceleration in the floor, you don't have, at least in our experimental test, never those tests maximum acceleration in the center, and this is not the case where you produce the maximum force on your panel. Okay, so you can get, I don't know, 0.3 G of PGA, PFA, okay, but you don't have the corresponding maximum values of the acceleration in the center. This is what happened there. Of course, I told you, it's not generalizing this. It's specific for this boundary condition, and maybe it's not for others. But we should take into account, I believe.
Paolo, just a small curiosity. If you assume that it is a homogeneous continuous in the linear elastic range, you can compute the frequencies depending on the boundary conditions of the out-of-plane enclosed form. You have tried that? How have you tried to compute the out-of-plane frequency in closed form solution, and how they align with the experimental results?
Yes, of course. You know, there is a secret here you have to compute the right values of modulus of elasticity and masonry, which is not simple, which is probably is not related to the modulus of elasticity that you get from compression tests. This is very new things. I'm not sure what I'm saying. There is this feeling. So if you get the right modulus of elasticity, you can get results which are very close to the results that we got from this type of test.
Thank you. I'm also looking forward for the guidelines. So at this stage right now, if you are to recommend a guidance or, I don't know, standard, whatever you name it, publication, something solid that recommends and guides you how to estimate the out-of-plane capacity and nonlinear response of infill walls, which one would this be?
Right now?
Yeah, at this stage that we are right now.
Literature, in the sense that you can get some results from Eurocode 6 for the undamaged panel for the evaluation of the plane strength, but there is no, I think, codes right now that indicates how to reduce this out-of-plane strength due to in-plane action right now. There are publications, scientific publication that you can reference to that. But the new Eurocode 8, the new draft Eurocode 8 will include it. Will include it with results more or less based on what I show you. So right now the only thing that we can do is that.
Speed up the publication.
Guido, maybe you can add something.
No, well, actually, the guidelines that you were referring to, that unfortunately are written in Italian.
Yeah, but I'm sure that we can translate quickly.
Yeah, I think that they could be a good reference considering the state of the art, in the sense that the guidelines were meant to provide a support to designers. So they go somewhat beyond what a code would say, and they could be unfair. But yeah, okay, we need to make
an extra effort.
an international version of it.
Yes.
Thank you very much. Thank you again.
Thank you. Thank you.
Very interesting. Okay, so now we can welcome the new speaker, Marcello Cademartori. He's a former student of the ROSE School. He graduated in 2007, and he is part of a RINA Consulting firm. He's head of the Bridge and Infrastructure Department, and he will talk about assessment of existing bridges as a perspective from recent experience. So the stage is yours.
Thanks, Chiara, for your introduction, and good morning all, and thanks to the school and Professor Monteiro for inviting me here to talk today. I'm quite a fan of this ROSE seminar because I think I've attended, all the years since 2013, but this year I'm in this side of the audience, so I'm quite excited to give you an overview of how the studies here in Pavia changed my professional career, but also my personal feeling of my activities and my life, I would say also. So I studied at the University of Genoa, something that I'm proud to tell you because of the good professors and good students I've met there. And in 2007 I started my activity in Da Polonia, that is now RINA Consulting in Genoa. And after a couple of years of activity, my first step was in 2009 when I was in a train commuting from my hometown to the office. I received a message that there was an earthquake in L'Aquila, the 6th of April, and I really felt that I need to do something for the town. And so I decided to go as a volunteer for the damage recognition in L'Aquila, and that was my first experience really observing the impact of an earthquake in real buildings and real bridges. And so after that experience, I decided to start learning something more in earthquake engineering, and this is why in 2011 was my first time here in Pavia for a short course in seismic isolation and energy dissipation with Professor Sullivan and Professor Calvi. So that was my first time here in Pavia. And 2 years later, Da Polonia, my company in which I worked, asked me if I would like to attend a master or something more advanced. And at that time, I didn't have any doubt, because my dream was to come here and to attend the master at the ROSE school. And so I stayed here between 2013 and 2015, and in that period I've met many colleagues from different countries of the world. You can see a map that we created just the last day of lecture because of the different students and colleagues that we have met from around different countries. And with some of them we are still, of course, in contact. We have worked together in different projects, and so that was really a very nice experience that changed really my life, not only from a professional point of view. So I did a thesis here at the ROSE School on displacement-based assessment of risk concurrent with bridges. So another dissertation on bridges because of my passion in this field. With Professor Sullivan and Professor Cardone, and I really learned a lot from that period in bridge modeling, seismic modeling, and we'll see something about that and how we have applied in some of the projects the concept that we have studied here. So in 2015 I came back to my work activity, and because of what I've learned during the period of a master here, I was involved in different challenging projects. I'll give you just some of the examples. This was a set of activities that we did for the seismic retrofit of existing bridges in the A14 highway in the central part of Italy, in which we applied seismic isolations and seismic retrofit with fiber polymer materials for different highway bridges. I had the opportunity to work also in some of the offshore structures in which we applied the concept of salt structure interaction and seismic design and assessment of steel moment resisting frame and in this project we really saw all the different steps of the seismic analysis, from the soil input at the non-structural components, so at the behavior of the piping inserted in the main steel frame. I had possibility to work in different research projects. Some of these projects were conducted also in cooperation with the Eucentre here in Pavia. The main framework of the research project in which I was involved, and I'm still involved, are related to the resilience engineering of transport infrastructure from the seismic point of view, from flooding risk and climate adaptation point of view. I did another very big experience for the seismic resilience of public buildings in Kyrgyzstan. We worked here for the World Bank, and we applied the concept of seismic losses. We defined the loss curves for the existing situation of the buildings and for the retrofitted conditions of the building. And in this case, just going back to the presentation that Mania did before, we were able to convey to the client the message of how the retrofit of the buildings was beneficial just with this kind of cost-benefit analysis, including the estimation of economic losses in our analysis. And of course, I was involved in the reconstruction of our bridge in Genoa after the collapse of the old Morandi bridge. And in particular, I was leading all the testing campaign for the seismic isolators and for all the bearing supports of the new viaduct in Genoa. And we came here in Eucentre in Pavia to test different seismic isolators. Some of these isolators were quite big, and at the end we did more than 200 tests for different kind of seismic isolators here at the Eucentre. Recently, in my activities, thanks to what I've learned again here at the school, we had the opportunity to participate in some important conferences. The European conference in Saloniki in 2018, and of course we had the opportunity to present some papers last year at the amazing World Conference in Earthquake Engineering that we had in Milan, and that was again a great opportunity to link my professional activity with a research activity and with academics, and to meet again different friends and colleagues from different parts of the world. I'm involved now in different programs for the evaluation of existing bridges, and so in this part of the presentation I would like to give you some of the peculiarities, some of the our perspective from the recent experiences that we are doing in assessment of existing bridges. So we'll see some of the practical considerations. We are studying more than 60 bridges, some in Italy, some in other countries, and these bridges are, this portfolio of bridges is mainly composed, more than half of the bridges are composed of precast, pre-stressed concrete bridges. Some of these are concrete arch bridges and ordinary reinforced concrete bridges. When we talk about bridge evaluation, we need to start from the Italian situation. So what we have in Italy now, so we have a road network that is composed by more than 50,000 kilometers just in highway and state road, 100,000 kilometers of other roads, and more or less 4% of these kilometers are covered by civil structures. So we have quite a huge amount of structures in our country. And more than 30,000 road bridges are included in the main road network, and more than 1,000 bridges are without owners. So these bridges do not have a real owner, because of different reasons. And we also have more than 18,000 railway bridges. If we look at the bridges period of construction, and this is one of the key parameters when we talk about bridge evaluation, we can easily see that more than half of the existing bridges that we have in Italy were built before the 80s, 24% before the 1961. And these years here, we'll see later, correspond with important codes that were released for the design of bridges, so quite an important parameter to be taken into consideration. The European situation is not much different from the Italian situation. Here we have a couple of examples. In France, after the collapse of the Genoa's bridge, they inspected more than 40,000 bridges, and 10% of these bridges required immediate attention, and more than 20% of the bridges need significant repairs, so are really in bad condition. In Germany, again, more than 10% of the bridges have a condition that are not satisfactory for the public safety, and we could see a similar situation in other European countries. We are working now also in assessment of bridges also in US. The situation again also in US is quite similar in a sense. They have more than 600,000 bridges, and about 1/3 of the nation's bridge repair work or replacement. And again, if we look at the bridges of the period of construction of these bridges, we can see that almost 40% of the bridges were built before the 60s. So this problem of existing bridges and of management of existing infrastructure is really a problem for Italy, Europe, and also for the US situation. When we talk about bridge failure and bridge closure, of course, we are not talking about only a problem of a structure itself, but a bridge is included in a road network or in a railway network, so a bridge closure or a bridge failure can negatively impact the behavior of a network, of course. So we have direct impact and also indirect impact. And just an example, for the collapse of the bridge in Genoa, we had a cost of reconstruction of about 220 million euro, while the indirect costs were about 2 million euro per day, with a total downtime, so the total period of bridge closure was about 500 days. So even the downtime was quite close compared to other situations, but the indirect costs were really, really big. Bridges collapse. Here we have collected some of the data of the collapses that we have in Italy. So it's quite amazing to see that starting from 2013, just because the database started from that. So in the last 12 years, we mainly have more than one bridge collapse per year. And this is not comprehensive. We had other bridge closure and bridge failures, but these are some of the main bridges that collapsed. Some of these bridges were included in highway, some affect road network, road state. Many of these bridges collapsed because of flooding or hydrological effect. Some of these bridges collapsed for problems related to deterioration, damage, and aging effect. So when we do bridges evaluation, we think that we don't have to lose the origin of our main goal. So this is what we would like to share also with you. So the basic concept behind the activity of bridges evaluation. So why we need to evaluate to assess a bridge. We identified, according to the international codes, 4 main points. So structural deterioration due to the time-dependent actions, and we have seen the age of our existing bridges. So corrosion, fatigue, degradation is one of the main reasons to assess the performance of a bridge. Structural damage by accidental actions is another point. The need for a reliability check after an earthquake or because of increased traffic actions, and this might be required by authorities, insurances, or owners because of their internal contracts. And then we have a case that is quite common about the change in use or extension of design working life. Changing use is quite common not only in Europe but also in developing countries, and this is now the case, for example, when we have a road bridge in which we want to build like a tramway or a metro line, and so we want to use part of the existing bridge to accommodate also a corridor for a new tram line or a metro line, and so we need to assess the performance of the existing bridge to understand if the bridge is good for use and if the bridge can accommodate the new corridor, for example. So we have some of the big questions when we start talking about bridge evaluation procedures. So what happens at the end of the nominal life of a bridge, and which level of reliability we have to use during the bridge assessment phase? Do we need to repair or replace a bridge that is not in a good condition? How can we collect the original data and the missed information? Which level of knowledge we have to obtain, and of course which loads we have to apply to existing bridges. One of the important things that we are recognizing looking at these activities is that it's impossible to create all the bridges that have problems with the same level of details. This is not, from an economical, temporal and technical point of view, this is not feasible. So we need a sort of prioritization scheme. And there are different prioritization schemes now in our Italian guidelines and also in different research activities, but still the prioritization of the investigation and of the assessment is one of a key point. So when we talk about assessment, and also in our structural team, we sometimes discuss about this. If you are a structural engineer and you are used to do design of a new bridge or design of a new building, and you approach for the first time assessment, I mean, things are not the same. You need to approach your project a little bit in a different way. Bridge ratings include a wider range of variables that is typical in design, and design may adopt a conservative reliability index, while in rating, an overly conservative approach could lead in load restrictions, rehabilitation, or even need for replacement. So in design, but even more, of course, in assessment, we need to find a balance between safety and economics. We have included here some nomenclature because we are doing different bridge evaluations in different countries worldwide using different international codes, and during our meetings we face sometimes some difficulties in use the current nomenclature, current terminology, and so we are trying to just list down some of the nomenclature that are available in the international codes. So when we talk about bridge evaluation, we mean the full process of assessment of the performance of an existing bridge. When we talk about bridge assessment, is the set of activities performed to identify the reliability of the existing structure, like for example the seismic assessment. So it's a specific activity that involves, usually involves numerical analysis. Bridge load rating is the specific activity related to the determination of the live load carrying capacity of an existing bridge, so for traffic load or railway load. The condition rating is more related to the identification of the condition state of a bridge, so in terms of the physical condition of the bridge as a system and of the bridge components. And the concept of reliability that is included in some of the guidelines and is the main part of the assessment process, that is the probability of success, no failure, in a certain time period, that is what we call the reference period. Bridge load rating, as we said, so is a specific activity of the live load carrying capacity, or the definition of a live load carrying capacity of an existing bridge. And this is the equation that we have in the AASHTO code, in the American code, and it's based, so the rating factor is basically the capacity of a bridge related to the live load. So it's the capacity minus the effect of the dead load minus the effect of a permanent load divided by the effect of the live load. And in the American code, for example, they consider the condition of existing bridge with this condition factor that depends on the condition of the bridges, and so the degradation is considered in this condition factor, and the American code is telling us exactly how to define this condition factor. And this might be a discussion also with the owners and with the client, which condition factor do we need to use. So when we talk about bridge evaluation in Italy, but also in other countries, we need to understand from a historical point of view which was the process of the development of the assessment and design codes, because we need to match the age of construction of a bridge with the development of the codes in order to understand which code the original designers used to design a bridge, if that specific bridge was designed or if it was just defined with best practices. So in Italy, the first reference was the guideline for the bridge inspections that was just related to inspections in 1967. And then we have the first code for the seismic design with some specific indication also for existing bridges in 2004 after the Molise earthquake in the 3274 document from the citizen protection. And in 2009 we have a first release manual for the seismic assessment of bridges with a full comprehensive procedure for the seismic assessment of bridges. But it's important to highlight that only in 2020 we have a release of a comprehensive code for the load rating in Italy. And if we see the three main codes that we are highlighting here were just released after tremendous tragedies that we have in Italy. So after the Molise earthquake in 2002, the L'Aquila earthquake in 2009, and after the collapse of a bridge in Genoa in 2018, and after that we had the release of the Italian guidelines for the bridge evaluation. And as we said, it's important to correlate the age of construction of a bridge with a change also in the load actions. Here we listed in a timeline the different codes that were used by Italian professionals, so the Italian designers, for the design of a bridge. And in all of these codes, the loads for related to the traffic actions were changing, and if we look at the increment of the loads in the different codes, we can say that in the period in which more than 50% of existing bridges were built, the distributed load, the surface load, and the axial load was lower than the load that we use now. One of the important date was the 1962, because it was the first code with concentrated load, with axial load similar to the codes that we are using now. Now, if we look a little bit in more detail, we have included here a couple of studies, a couple of examples, just to understand that if we consider like a bridge that was built between the 60s and the 70s, and if we consider a regular span between 25, 30, 35 meters, so some of the spans that are very, very common in our cases, we can see that in general, the major effect in our assessment is not due to the change in the load actions, because the ratio between, for example, on the right part of this slide, the ratio between the bending moment of the old code and the bending moment of the current 2018 code is bigger than 1 in that range of the spans. So in that range of spans and in that, for those bridges, in general, the major effect that drives our assessment process is the degradation, so the condition state of a bridge, and of course the reliability that we are going to use in our assessment, and that is asked by the different code. If we look at the situation about the different guidelines and codes that we have, the current situation of the Eurocodes, we don't have specific indications for bridge load rating. We don't have specific indication of a seismic assessment of bridges, but we have a single document in the Eurocode 8 dealing with seismic assessment of buildings. The next generation of Eurocodes, as also Paolo was explaining before, is going to help us, we think, in some of our practical activities. And we know that there is a big working group that is dealing with assessment and retrofit of existing structures, so building and bridges, and we should have more detailed indications for the assessment of existing structures in all the different Eurocodes, so concrete, steel, and so in different materials. And so the assessment procedure in the Eurocode should start from the beginning, so in the Eurocode 0, so in the definition of the assumptions, and following all the different detailed Eurocodes dealing with the specific materials. So we think that the Eurocode next generation is going to help our activity. One of the reference code that we are currently using is the Ashtor Manual of Bridge Evaluation. The first version was released in 2005. The code introduces the concept of real loads and real traffic lanes, that is quite important in the bridge evaluation. The Ashtor code introduces the target reliability levels, so it's specified which reliability you are going to use during your assessment procedure. It's clearly stated the load rating procedure for different technologies, so for different bridge typologies, and includes different bridge typologies from concrete, steel, and steel concrete. So we would like to show you some practical considerations based on our experiences that we are doing now. Some of these are quite obvious, but some of these are not so easy to be implemented, and especially to be conveyed to the owners and to the different stakeholders. And what we call the step 0, that apparently is quite an easy task, but it's not, it's the data collection phase. And this is quite a really important part, because when we assess an existing structure, and of course also for an existing bridge, we need to identify if we have the original design. So if we are able to find the original design, we need to ask for inspection records, of course. We need to understand if a bridge was modified during its life, so if there was intervention or any impact, and we need to collect all the historical data of the bridge. So we call this data collection and data review. So this is the first step in any kind of bridge evaluation and bridge assessment. So the step one is that after you collect all the data, is a detailed assessment needed or not? So based on the different regulations that you are going to use according to the different countries, a detailed assessment is needed according to the main points that we have seen before or not. If a detailed assessment is needed, the first part is to perform some preliminary by hand calculations just to identify the load path of a bridge and how is in general the behavior of a bridge. And this can be quite straightforward for like girder bridges, but is not always the case. So after these kind of preliminary by hand calculations, we need to go to the testing campaign and then to the assessment results and discuss the results in the decision phase with the different stakeholders. So as we said, we discussed about the importance of the original data, so geometry, construction details, and material properties. And one of the big questions is whether the original design is available or not, because if it's available, we can proceed with the testing campaign just looking at checking the details, while if it's not available, it's really, really difficult to perform a testing campaign and to obtain reliable results. And one of the elements in the ASHTO code that can help us is the proof load test, that is included in the ASHTO code as alternative to the analytical models, while in the Italian guidelines is not still included as alternative measure, but it's considered only as temporary measure. So I'll just go to the end. So the importance of the original data and of the materials. So it's important to check the results of the testing campaign with the literature data that we have about the materials, because especially for the steel reinforcement, we have quite a huge database of the materials. And one of the important things in our procedure is what we call the performance-based testing campaign. So rather than a prescription, just follow like a performance approach in our testing campaign. So go and inspect the details and the material that are really critical for the bridges. We have accessibility issues when we define the testing campaign. If we think, for example, to spans above a railway line, caisson bridges, and we have also the problems of a degradation identification that, as we said before, it's really important in the bridge evaluation to identify the degradation in the different elements of a bridge. We don't need to forget the non-structural details in the bridges, because in most of the cases the degradation is due to wrong details and lack of maintenance, for example, of a raining water collection system that is not adequate. And this creates damage in different, degradation in different elements. And regarding the seismic behavior of an existing bridge, one of the important thing, or the more important thing, is the identification of a support condition. And this leads sometimes to also the need for identification of lower bound and upper bound behavior of a bridge, and we can use also some simplified calculations to identify the overall behavior of our bridge system. So just to conclude, what we think are our lessons learned is that we need a sort of prioritization in order to identify the bridges that are most critical with highly daily traffic, essential freight corridors, and serve also as evacuation routes. We had recently an experience where an existing bridge was included in an evacuation route, but the bridge was definitely not appropriated for that use. We need to encourage inspection, maintenance, and preservation for the bridges in good condition, because we need to avoid that bridges that are currently in good conditions go in very poor condition as the time proceeds. The detailed assessment is a very onerous procedure, and again, we need a prioritization procedure because we cannot approach all the bridges with the same level of details. The importance of international references and experiences that can help us in some of the details. And of course, very complex models that we are used to create need to be validated by sanity checks and by hand calculations. We need, for seismic assessment, especially to encourage the use of nonlinear procedure, and for example, the use of displacement-based assessment that help us a lot in some of the recent projects that we are, in which we were involved, and really the importance of the efficiency of a testing campaign, because the testing campaign has a problem in terms of time, cost, and traffic interruption when we talk about bridges. So these are the main lessons learned from our recent experiences. So thank you very much for your attention. Sorry if I take long, but thanks.
Thank you, Marcello. I think we have time for one quick question, if are there. Professor Calvi.
Thank you, Marcello, for your comprehensive presentation. I'd like to raise three minor issues. One is referring to when you were showing that it is in the fact that after all the loads have not increased that much over the decades, and this was clearly referring to the intensity values. But I wonder whether you share with me the fact that most relevant point could be fatigue or the repetition of loading that was not mentioned. Second point is that related to deterioration and so on, what scares me more now is the condition of post-tensioning cables. I'm really worried when I have to deal with a bridge with post-tensioning cables after it became evident that the density of the post-tensioning steel in the duct in the 50s and 60s was maybe 1.52 times the density of today, and the injection material were poorer, or anyway less fluids. Therefore, it is very easy to have problems of injections in the cables and problems in the heads for post-tension. Finally, it's very minor. The Ordinance 3274 was issued in 2003, not in 2004.
Thanks, Professor, for your comments. Yes, for post-tensioning, I mean, we are doing assessment of different bridges with the identification of a real condition of post-tensioning cables. It's a very onerous activity, and we have some of the cases in which we don't have the original design of a bridge. So in those cases, it's really, really difficult to arrive at reliable results. I mean, the owners of the bridges, they don't have any drawings, any calculations, so the testing campaign is really huge, and I don't know if it's going to arrive at the real results. Thanks.
Thank you very much, Marcello, again. And I think now we can close the session and we can go for lunch.
Okay. I think we're ready. I think we're ready to get going. Just take your seats, please. Thank you. So it is with great pleasure that I now start this afternoon session of the International Nigel Priestley Seminar, and it's even with greater pleasure that I introduce the keynote speaker of this year's seminar. And keynote speaker is Professor Alessandra Marini. She's a professor of structural engineering at the University of Bergamo. And as you will understand and appreciate from her talk, she's a true pioneer for what concerns issues related to sustainability, circularity, environmental impact, life cycle thinking. And I say that with no hesitation or doubts. She really is a pioneer because she started working. These subjects are subjects that nowadays we've all learned to consider. We've heard from the presentation of this morning of Michele Palmieri how a design office, a design company like Arup is adopting and taking these issues very seriously. Alessandra Marini and her research group were proposing these things 10, 15 years ago, and they were such a novelty that they could not find a journal to publish the work. Every different journal they would submit the papers to would say, this is outside of the scope of our journal, because one journal was focused on structural engineering, the other journal was focused on environmental impact, the other journal was focused on circular economy. And it took them quite a lot of patience and persistence to finally pass the message that we now live in a new age, a new paradigm, a new mindset that has to consider all these things together. And Alessandra will certainly further expand and illuminate you all on these aspects that I can only grasp. Alessandra, the stage is yours.
Good afternoon, everybody. It's a real honor and a pleasure to be here today in a day that celebrates academics excellence, and also, given that you defended the young researcher defended their thesis, we are also celebrating the future of our discipline. First of all, I want to thank Rui for the nice word and invitation, and also Ricardo Monteiro for inviting me here today. And I extend a warm congratulations to those young researchers who have been recognized today. So the title of my presentation is Shaping the Sustainability Transition, Challenges for Conceptual Structural Design. It speaks to a tension that some of us do feel lately. The times we are living are times in which a change is unavoidable, and the climate crisis, the depletion of resources, the growing demand for social equity, and for social justice also, it requires new answers. So we cannot consider those minor peripheral problems. They are core central issues we need to tackle. And my point here is that as structural engineers, with every single design choice we make at the early stage of the design can indeed shape the transition we all need for a better future, for ensuring a better future for ourselves and for the generations to come. So where do I start from? I start from this. More than 55% of today's building will still be standing in 2050. That means we're not starting from scratch. I'm talking about the existing building stock, and I'm focusing on building for the example I will carry on during the presentation, but of course it works for infrastructures as well. The environment, the built environment I'm talking about, it has figures which are well known by everybody. 50% of the European building stock is 50-year-old or more, and it's fragile and has lots of vulnerabilities to many types of risks. And it's also impacting throughout the life cycles, and it's impacting in energy consumption, gas emissions, and material depletion, raw material consumption. And furthermore, the climate change is exacerbating vulnerabilities, not only environmental vulnerabilities, but also structural vulnerabilities. And both vulnerability and impacts actually shape the ecosystem we are living in. So that's where we start. We need to tackle all these deficiencies. We need to take care of the built environment considering all these aspects. And the point is, as structural engineer, how can we contribute to this? Let's start from the general framework we can make reference to. Well, the Sendai framework calls for risk and disaster reduction, and on the other hand, we have the Sustainable Development Goals, which in a way are picturing the choices, actually the objectives we should follow to ensure further generation to thrive and not to suffer from the decision we are taking in this day. And moreover, we have decarbonization targets set for 2050 and a strict carbon budget that we can use. So from the intersection of these two general framework, an idea stands out, and its sustainability is not a single objective. As a matter of fact, it's the balance of many. Oops. No. Is it everything okay? Okay. Good. So I was saying that both these roadmaps share this, enable us to build up this idea that sustainability, it's actually the balance of many objectives: safety, resilience, reliability, eco-efficiency, comfort, and equity. And if we have to target all these major performance objectives, we need to reckon with the built environment in a new way, in which structural engineer will broaden the spectrum of responsibilities. And within this context, within this scenario, unfortunately, that's the way it is. That's the way we still carry out our interventions. Major interventions are basically either structural or usually they are targeted towards eco-efficiency, disregarding vulnerabilities, and the little foresight of this kind of intervention is quite clear. And these kind of intervention are also granted by national financial incentives, and most importantly, they are perfectly compliant with sectoral code, and that's probably one of the problems. We do work with sectoral code rather than with a more comprehensive and multidisciplinary code. Moreover, the renovation rate is well too low, and there are barriers to the renovation basically related to the need for inhabitants displacement, building downtime, temporary building downtime, and major initial cost of the intervention, which prevent larger major renovation action to be carried out. But by the way, if we continue this way, we are not going any further and we won't achieve those quite challenging target established by the European Commission as far as decarbonization is concerned. But allow me to make a little bit of a detour. This is a little bit of litter on the grass, and this is a photographic project which I like a lot. It portrays a nice family surrounded by the garbage produced in a week, and here in 4 years. It shows us that small little actions which appear to be harmless. If they are repeated daily and they accumulate, they can scale up to something overwhelming. And that's the same thing for building. Buildings are the result of hundreds of decisions, and they can scale up. As a matter of fact, fragmented actions can impact the environment quite remarkably and might create non-resilient environment, undermine climate goals, deepen systemic risks, and consequences that we might suffer are not just technical side effects, but they shape the ecosystem, the social equity, and the generational justice. So what should the engineer do to participate in the sustainability transition? We really need not to postpone any further. Well, the contribution of the structural engineer is to broaden the spectrum of responsibilities, as I was saying before, and trying to work in a combined way to target all those multiple principles I was mentioning before about safety, reliability, and eco-efficiency and comfort and equity at the same time. So in a way, we need to merge and carry out risk-informed green transition on one hand, which is more close to our spectrum of responsibility, those we are more used to, but we should also carry out sustainability-informed risk reduction. Taking a little bit of time to evaluate the long-term effect of every single choice, of every single structural choice we make. So this is kind of a new awareness, not a new awareness, but the awareness we should all take is that structural design is not just structural, it's environmental, social, it's ethical. And my point here in this presentation is that sustainability is shaped at the conceptual design stage. That is where values take form, decisions define long-term impacts, and also trade-offs are negotiated. That's the point, that's my key thesis in this presentation, and what should we start doing rather than focusing on snapshots and ensuring safety and reliability and structural performance objectives we are more used to. We should expand our view from snapshots to the entire building life cycle, and we should start see buildings and infrastructures as complex organisms evolving and aging over time in a dynamic context which also changes over time, probably and possibly. It might be exacerbated by climate change and so on and so forth. And buildings throughout the life cycle impact at the environmental level, at the social level, at the economic level on society. And throughout the building life cycle, we need to ensure multiple performance, as we will see in a minute, but we need to guarantee resilience, safety, together with eco-efficiency, comfort, and functionality. So what we need is a life cycle approach to govern the generation of impacts throughout the life of the building, and also to govern the performances we are requiring to the building. And let's be a little bit more concrete. And talking about impacts, let me show you this slide which shows the embodied carbon of a building. And on, nope, let me try to see the pointer here. There it is. So here you see that considering, of course, impacts are strictly dependent on the building typology, the age of the building, the technology implemented in the building. But considering medium-scale residential building already subject to energy amelioration measures, we might see that the embodied carbon, the impact which is embedded in the material of the construction, is a quite large share of the environmental impact. On the right, you see that the structure in the embodied carbon, the structure plays a major role, because upper floor, foundation, frame pilings do take something about 70% in other for other building typologies, up to 80% of the embodied carbon. That means that every single choice we make in terms of building typology, technology will impact, will be associated to a certain amount of embodied carbon. And here is interesting to note that the larger share of embodied carbon is in the foundation system, particularly when micropiles are used. Those are responsible of the largest share of embodied carbon in the structure. So the mitigation strategy might be reducing the upfront embodied carbon, and we will see how we can do that, but also increasing the service life, either of the structure, but if the structure cannot withstand any increasing the service life, we can increase the service life of the components of the building. That means go for a circularity approach, so we do not extend the service life of the entire building, but the service life of each single component. And so if we have these major principles that we want to achieve safety, resilience, and reliability, how can we do that? At the early design stage, we can introduce sustainability-conscious design objectives, new sustainability-conscious design objectives, which can inform the conceptual design phase, together with the performance objectives we are more used to, like safety, resilience, and so on and so forth. We might decide to go for design for material eco-efficiency or design for sustainable and safe construction site, to reparability, flexibility and adaptability of the construction, for easy maintenance, for durability, for example, which is really important, and also, and we are up at the end of the life cycle, we can enforce design for deconstruction, reuse and recycling, and for sure, reduction of waste. And the last three design objectives can be grouped into one major performance objective, which is design for circularity in the first place. So you see, from construction, actually production stage to construction stage, and then to use and until the end of the life cycle, and even beyond the life cycle, we can enforce all those performance objectives and see if these performances shape our structures differently. Of course, I need to mention that for ancient historical buildings, we have a performance objective, which probably is the most severe one, which is designed for preservation. And as a matter of fact, that might guide the entire design. But talking and referring to other buildings, actually, the majority of the buildings in the outskirts of our cities, these are major performance objectives which could help us quite a lot. Of course, adopting these sustainability-conscious design objectives in the early design stage might end up in new design strategies we might propose, and also it results if we use these design objectives ex ante, we might end up conceiving new techniques, adopting new materials, or even re-engineering existing solution towards sustainability. And furthermore, we can use new structural schemes, new modeling strategies, new structural details, business models, and of course this is a great opportunity for innovation that we are experiencing nowadays, but it's also something for which major research is needed. Of course, at later, I'm sorry, I see that the slides are not working fine, but anyway. Of course, at a later stage, we will be able to use more refined tools, such as sophisticated performance-based design evaluation method, but none of those methods, life cycle assessment, life cycle costing, social life cycle, whole carbon life cycle assessment, or loss analysis, and so on and so forth, neither of those can compensate for a suboptimal initial conceptual design phase. The adoption of a sustainability-informed life cycle perspective and life cycle thinking approach also require a systemic design decision-making approach. That means that we need to overcome the traditional approach in which we evaluate the construction at time of construction and make sure that the construction cost is minimum, and we should broaden our perspective to evaluate environmental benefits and social benefits and economic benefits at time zero, at the time of construction, throughout the life cycle, both at the building scale and at a larger scale, which could be at the infrastructural level. Of course, this approach comes along with some trade-offs because the optimal solution does not exist. We will always have to establish and negotiate trade-offs. A solution, we can have trade-offs between life cycle stages or environmental categories or sustainability pillars. For example, a solution which is optimal from a technical point of view is too expensive and so is not adoptable, is not viable. It won't help us increase the renovation rate, which is one of our major targets. On the other, or furthermore, we can have trade-offs between regions. We might have local gains, but global impacts, or between generations. We might have today's savings that might impact on tomorrow's costs. Let's dive a little bit more into the new sustainability-informed design objectives. So at the production stage, we might design for eco-material, for material eco-efficiency, and that means that we try to reduce the environmental debt at the very beginning of the design. Imagine two buildings, same identical performances, but the one is made in a traditional way and the other one is trying to implement a new material, more efficient material from an environmental point of view. Of course, at the end of the life cycle, those buildings will perform quite differently, so it's only the structural performance which is the same, but in a systemic approach, differences are quite apparent. Actually, this is also important. I told you before that waste is not an option in this systemic approach. We need to reduce it as much as possible. We will see design for reuse. I mentioned it before. Sometimes reuse is not possible, so eco-material help us in having the possibility to recycle the materials at the end of life. So this point, design with eco-friendly material from reuse, second life material, things like that, can be very helpful. But then shifting to the construction stage, we can design for constructability and low impact construction. That means imagine two construction sites where we walk by construction sites, we are used to traffic disruption, noise, dust, and imagine another construction site in which construction is completed in half the time, less noise, less pollution, so less impacts on people, on the environment, on society, on biodiversity, for example. And how can we do that? We can go for industrialization of components. So off-site production could be quite helpful, could allow us to control the quality, and prefabrication could be another option to consider to reduce impacts at this design stage. Prefabrication and off-site production also reduce construction time, allow and enable safer working conditions, and of course we need to imagine the building as dry assembled, and that will in turn result in a cleaner construction site. That, of course, in that systemic approach could require higher expenses to be spent in the very first place. But again, in a systemic approach, one can decide whether it's a viable option or not. This is the way to go or not. And if we always stay on construction stage and use stage, We can design for retrofit feasibility, for example. I told you we have barriers mainly related to the need of relocating building functions, even if temporarily, and initial costs can be high. So lately of course not for listed building, not for historical building, but exoskeletons have been proposed which can be assembled outside the building without any building downtime. And this can be a viable option to make this intervention more feasible. When working with exoskeleton, we can work on the structural scheme. We can play around a little bit with the structural scheme to see if we can reduce impacts. So for example, we can go for a shear wall exoskeleton or a coupled shear walls exoskeleton. We can push even further up to shell exoskeleton. The largest the shell exoskeleton is a second, it envelops the building, and by exploiting the dimension of the facades enables us to reduce the foundation quite remarkably. For example, we can reduce the number of piles and we know that piles are the generator of large impacts and large environmental burden. Or we can even move a little bit further and we can attach the shell to the building. For those cases in which this solution works, of course, these are not always feasible from a technical point of view, but sometimes we can decide to attach the shell exoskeleton to the foundation of the existing building and exploit the dead load of the building to stabilize the exoskeleton. But exoskeleton cannot be even considered an option when the floors, the existing floors are not capable of triggering a diaphragm action. Sometimes we need to reconsider, for example, in this case, we need to reconsider the location of the shear walls. In this case, it's a shear exoskeleton. We decide the inner space between shear walls to make sure that we won't have any problem in the existing diaphragm. Because if we needed to strengthen the diaphragm, not always, but often, we would need to relocate people and work with diaphragms. Of course, we can work also with intrados, dry assemble diaphragms, but again, it can be a burden. Then we move forward, we move to the use stage. What do we design, what do we need to design for time and evolving performances? The structure we are designing might be hit by an earthquake in 50 years. Are we sure that it will behave as designed? Well, we need to consider time in our structural models. We need to consider decay of materials. And also we need to consider the dynamics of the context the building is inserted into. And of course, if you consider time and we consider decay, we have to reckon with uncertainties, which expands tremendously in this case. And then we need to consider also, and to be able to model maintenance work and the effect of maintenance works. And of course, this kind of new structural model will benefit quite largely by monitoring, long-term monitor, multi-performance monitoring of the building to support preventive maintenance, strategic retrofit planning, transparent sustainability metrics. Again, talking about exoskeletons, let's consider the design for the reparability and continuity, meaning thinking that after an earthquake, schools are reopened, buildings are still lived in, and businesses bounce back to normal right after the event. To obtain such a goal, we should work with performance objectives, and for example, we might ask stricter performance objectives like operativity at life safety limit states, ductile behavior, and lamp damage for near collapse limit state. And we are Professor Calvi was a pioneer in this performance design and also in this attention paid to non-structural elements, which becomes really critical when thinking about life cycle thinking as a perspective, as an approach to be adopted in the design phase. And to obtain those performance objectives, we might ask for stricter design targets. So for example, if we want to reuse to use the structure right after, we need to have zero residual displacement and of course protection of non-structural elements, and make sure that we control the maximum shear action which is transferred across the floor diaphragm. As for the technique, we might adopt adaptive techniques which adapt as in reaction to the intensity of the earthquake, and we might go for recentering systems, which enables us to obtain zero residual displacement. As for construction details, we might implement seismic fuses, places in which components into which we localize damage and that are easily replaceable after an earthquake. This kind of conceptual design might conflict a little bit with the need to optimize materials, optimize cross-section, but in the end, once again, it's a trade-off. We need to consider many aspects before defining the intervention. Then we have design for flexibility and future adaptation, which is also critical. Is the building future-proofed when we evaluate it? Needs might change over time, and performances might change over time, so we need to adapt the building. Sometimes increased design loads might enable to guarantee a longer service life and increase the potential of resale of a non-residential building, because it would enable changing the final use of the structure. In an exoskeleton, we might enable plugins to be attached to the structure, or even an upper floor, and possibly the resale of the upper floor might compensate a little bit for the initial cost of the construction. That could be an option as well. And also we should think of the service life of the structure. Should we be thinking of 50 years, or should we expand it, and what are the implications on the structural design? And then we come to this design for reuse and circularity. Buildings are usually constructed to be demolished, not to be reused. So imagine a building which is modular, which can be disassembled, and components can be, like Lego pieces, can be tracked, certified, and be ready for second life. That would be interesting. That would be an interesting option. But of course, for reuse to be feasible, we need standardized connection, exactly like plugs. We have to exchange electrical appliances. We need to have standardized connection if we want to reuse a single component. So there's a lot of research. We are actually carrying out this research with the University of Pavia on standardized plug-and-play reversible connections, because we need to deconstruct first and then reuse. So to deconstruct, we need reversible connection, and to reuse, we need standardized connection. Again, even if the structure is designed for reuse, it also has to be designed for recycle. As I told you, at one point, decay or something will require dismission of a component of a building and whatever. So if waste is not an option, we go for recycling. And once again, modularity may conflict with upfront initial costs and upfront initial embodied carbon. And then again, we need to carry out systemic evaluation. Sorry for the slide. I cannot understand the reason why, but by the way, what kind of future does a design for enable? This is the major question we should ask when we are carrying out the initial conceptual design. Design objectives, as I'm mentioning here, are not accessories. They are new ethic of design, where technical choices reflect deeper responsibility. not just to code, but to people and to the environment. And then we have this design for incremental implementation. This is a design approach which makes sustainability more accessible to a larger public. That means if a single-step approach, meaning we carry out the entire intervention and achieve the target performances, is carried out in one single step, it might be too costly and not affordable for a large share of the population. So we might decide to go for an incremental implementation. We we go for a phased approach, and we improve the building performances over time. And often we can combine the phased intervention, the step of the incremental intervention, with scheduled maintenance works and so on and so forth to minimize the global cost. This could also enable essential performances to be affordable for a larger public. And this is, of course, very in line, very compliant with the demand for equity, social equity, but it's also to the sake of resilience. If we have two buildings which are super buildings in terms of performance in a city, we're not actually obtaining much. If we can, for example, move all the city to an essential level, that would be a risk reduction, an effective risk reduction. So, as you see, it started out as a measure to offer the opportunity to a larger public to attain safety, for safety not to be something affordable to few, but to many, but it ends up being something very interesting for a major scope which is relevant for all of us, which is resilience at a larger scale. And of course, sorry, I go back a little bit, if we were able to use reused components, we might reduce the cost even further and make even higher performances accessible to a larger public. And finally, we have this re-engineering of traditional solutions. This is also very, very important, as no abrupt phase-off should be considered. Not long ago, I was on the other side of the spectrum. This is not sustainable, let's have an abrupt phase-off. And then I came to think that this is unsustainable for those families and communities relying upon those businesses. So what we need, as a matter of fact, is a sustainability transition, not a phase out and a switch, and a rapid switch. So as engineers, we can use the life cycle thinking approach to analyze a possible solution, see if it makes conflicts along the life cycle, see if we can improve something for the solution to be further engineered towards sustainability. And so we can support companies and preserve local economies through progressive re-engineering. Well, these are just a few examples of these performance objectives in practice. So what we have to do to design at the conceptual design stage to account for these sustainability-informed performance objectives. But of course the engineer needs something to shift, to move, to progress from conceptual design to the full design of its project. And then we need also examples of applications to see that this life cycle, not life cycle, sustainability informed life cycle approach and systemic thinking and systemic approach in the evaluation and management of building is feasible. What do we have? What are the tools that are available to support sustainability-informed life cycle thinking-based design? Well, we have policy documents. We have very many, particularly for the energy efficiency, improving energy efficiency. And then we have green building rating systems. But these are all ex post evaluation tools, not ex ante, not to be used initially to inform the design, to inform with sustainability the design. And then we have this sectoral code with no overarching sustainability frameworks. And of course, at the very top here, I try to show how the structural design progressed over the years. We started with risk reduction retrofit, then we came up to integrated retrofits, possibly energy plus structural efficiency amelioration, and now we are right here. We are exploring a totally different context. We want life cycle thinking based solutions. And then we have the contribution of research. There are very many projects which have been started lately that are trying to come up with tools to be adopted by the engineers to support the design. We have LCT design frameworks, indicators, assessment tools, re-engineering examples, novel LCT-based techniques, supporting circularity, and then also projects financed by the European community, and all of them are providing this critical mass of information which will soon help us producing something which is really what we need to foster LCT-based design. And then a very quick example of a framework. There are very many frameworks produced lately by researchers, but basically they're all made of 5 major steps. In the first one, we have the holistic assessment, not just structural, holistic assessment of as performances of the structure, and in this phase, the baseline performances are defined, the context is analyzed, barriers will emerge, and this will inform the very initial stage to see what we can do and what we cannot do. And then we have the second phase that I wanted to emphasize this. This is the pre-screening of possible eligible techniques. This is critical, and many researchers are working on this. We can see if solutions are compliant or not compliant with all those sustainability-informed performance objectives I was mentioning before. So we have multi-criteria decision-making matrix that can be adopted, or we might have methods based on optimization. We have very many solutions for this. There's not a general consensus nor an agreement to guide the designer. I just want to share with you the idea that there's a scientific community which is doing a real great job, and possibly we will be able to come up with a solution which could be also adopted by finally a code supporting integrated design, LCT-based design. And then we move to preliminary design, where we can adopt performance design methods and new performance objectives, new design targets, which are not attached, but bound to the sustainability-informed targets. And then we shift to decision-making, and here we apply all those instruments which are more refined, LCC, LCA, and so on, loss assessment, and so on and so forth. And finally, we have the selection of the optimal solution based on classification and ratings, and also integrated indicators that might enable the selection of the solution. This is interesting because the rationale of these frameworks is always the same. We start using indicator of performances and of sustainability in a qualitative way, meaning indicators guide more than they measure at the very beginning. But then while we slowly progress through the design stage and come up with a solution, we finally can quantify them and come up with the classification in the end. And what else? I wanted to share, do I have? time, yeah. I would like to share with you a few examples of application. These are not perfect, definitely they're even not complete, but they are pioneering experiences where we try to apply the sustainability-informed life cycle thinking in real application. This is the case, this is the ADESA project. The project we started in 2017, but then the construction was done in 2020. It's a gym hall, a prefabricated building, suffering from structural problems and very energy demanding. We assembled a multi-layer hybrid shell exoskeleton made of CLT panels, steel frames, and concrete cladding panels, as we will see in a minute, for energy, for improving energy efficiency, functional efficiency, structural performances. And we use this multi-layer exoskeleton in which every layer served a different function, and they are all dry assembled and and the design is carried out for the construction. And we have the architectural or finishing layer, which is conceived as the cover of a mobile phone, so we can switch it, changing the result completely from an aesthetic point of view. And then we have the fire protection layer, energy layer, structural layer. And here you see the structural exoskeleton I was mentioning, it's hybrid. On the short side, we had CLT panels with steel frames entirely off-site produced and shipped to the construction site where only the assembly was made. And then in the long sides, we exploited the existing, we rearranged, we re-engineered the cladding panels by introducing connection for those cladding panels to serve as one of the longer side walls of the shell exoskeleton. And here you see some pictures. We tried a tentative, this was a tentative trial of standardized connection. We weren't very successful at that, but we designed for easy assembly and fast deconstruction. And so not only we designed the phases of construction, but also the phases of deconstruction. We implemented structural fuses, and here you see the example of prefabrication with components shipped from off-site. And here is the longer side where we arranged the existing cladding panels through this structural detailing, enabling fast assembling and dismantling. On top of the shell, we needed a roof box structure to strengthen the shell exoskeleton. And this is the result. The community was so satisfied that they started a crowdfunding to finance the basketball court, and so this was an example in which the structural intervention, which was needed in the first place, triggered energy efficiency and also social benefits for the community, having this very small example of urban regeneration. This is a further example in which pretty much the same technology was further implemented with a monitoring system and incremental mechanical, electrical, and plumbing deployment. And this is a residential building. In this case, we weren't able to build the shell exoskeleton because of the lodges at the corners, which didn't enable us to attach the sides of the shell. So in this particular case, we went for coupled shear wall exoskeleton. And here you see this map system, which is very interesting because it follows the philosophy of the incremental implementation. Due to budget restriction, we were able only to mount a piece of it, not all of it, but the map system is entirely inspectable from outside with no demolition of the finishing, so it can be implemented over time quite easily. And then there was this monitoring system. In this particular case, once again, we worked for deconstruction, and so the concept of the design for the reuse for the construction and reuse of components was also carried out. We re-engineered the connections to the foundation, and then we introduced the structural fuses. All components are disassemblable, easily disassemblable. And this is the result. This stripe you see here is the covering of the map system I was showing before. As you see, is easily accessible from outside. And finally, this is another example, a modular reversible steel exoskeleton for circularity. This is only at construction document stage. These are residential buildings, large residential building of social housing. And in this particular case, we arranged the exoskeleton with these Lego-like components, modular and Lego-like, few pieces which are used to compose every single couple shear walls. And these also streamline the logistics at the construction site, because we just have 4 pieces which can be shipped where necessary. What was interesting here is also that in the very first initial stage, we decided we couldn't go for the exoskeleton provided that the floors were unable to trigger a diaphragm action. So in this particular case, we introduced external diaphragms, and those external diaphragms are expected to become balconies, and so they increase the value of the building. So, major contribution of this presentation. Sustainability starts with a question: what kind of legacy we are building for future generations with every single design choice, structural design choice we make. The buildings we are building will outlive us. They can either lock in vulnerabilities or enable resilience. They can embed large impacts or streamline eco-efficiency. Is up to us. Conceptual design is not code compliance, and my major point is that conceptual design is not a neutral act. It has consequences if we are aware of them or not. It is a decision of responsibility, of ethics, and of imagination. So my invitation here is for the young researchers to try to reframe the research you're working on in this sustainability-informed life cycle perspective and see if something changes. Reframe it, try to explore possible new questions that may arise. And sometimes it's the way innovation starts, by reframing something. And in my opinion, also us as academics are challenged and also called to action. In my opinion, multidisciplinarity, systemic thinking are no longer optional. They should be thought, should be used to teach and thought to the new generation engineers, because in my opinion, the complexity of the world we are living in requires multiple competencies and cannot be solved within the boundaries of a single discipline, or a single method. So let's act now. To shape the transition, we must first choose to embrace the challenge and contribute. Thank you. I hope this is of service. And just 1 minute. Let me acknowledge all the beautiful group of researchers I'm glad to be working with. Some of them are here. All these people are passionate about this subject, but we need to engage more and more researchers to tackle this challenge, which is quite remarkable. Again, thank you for your patience.
No, thank you Alessandra,
I'm sorry for the slides, by the way.
well, I take also some responsibility for that. I should have take good care of checking that there were no problems with the fonts, but the presentation was very clear and extremely inspiring. The fact that you were able to show not just the concepts, but also the actual practical applications in a series of case studies really means that this can be done, and this is really inspiring. You were mentioning in your final words, you were alluding to the younger generation. I think you're also inspiring for the diversely young generation. So thank you once again for that. Thank you.
Thank you.
Okay, so Ricardo, perhaps you want to join so that you follow up afterwards. So the last, as you've seen, the last points on the agenda before we pass on to the graduation ceremony is just a very brief account of or overview of the activities of Eucentre, the ROSE School. And so for Eucentre, that will be down to me. And before I start talking about very briefly of what we've done in the 2024 year, just a brief, I will not go through this plot in detail, but this is just to show that, to remind or to inform those of you that were not aware of, the Eucentre Foundation, it all started with the ROSE School. So the ROSE School was the seed that was planted back in 2001, and the Eucentre Foundation followed that seed. So it all started in 2001, and many things happened between 2001 and now, and some of them you see the inauguration of the Eucentre was in 2005. That's when we inaugurated the first lab. In 2009, the GEM Foundation was created, and I said I would not go through this in detail, but as I mentioned before, many things happened, and we had a new shake table built and inaugurated. You see it there in the year 2017. And in 2024, we've organized the World Conference on Earthquake Engineering. And that was certainly the highlight of the year. And I'll get back to that in a minute. But before that, just a few numbers of what the Eucentre Foundation has been up to. And it is with great pride that I can describe these numbers for you, or show you these numbers, because it is really impressive, even for someone like myself that follows the foundation on a daily basis, that we are able to do so much. And this is all thanks to the people that work at the Eucentre Foundation. This is all people-centric merit. 84 applied research and experimental lab projects that are typically done under the request of companies from the private sector, and we're extremely proud of that. And again, coming also back to the point that was touched before by Professor Marini, but also the presentations of this morning, the connection between a research institution and the private sector is fundamental. And the numbers show that. We are extremely engaged by the private sector. Almost 40 national and international research budgets funded either by the European Commission or national public funding. We continue to host students and visiting scholars at Carr College. We're involved in training courses for practicing engineers. We continue to support the PhD program with scholarships, a large number of scholarships, PhD scholarships, granted every year. I don't know how the researchers at Eucentre managed to do that. I'm always impressed. I'm always extremely proud of them. But notwithstanding this huge amount of projects, And for each one of those 38 research projects, you must think that there have been at least 100 research proposals that were submitted and only 38 funded. So I don't know how they managed to find the time to then also write scientific publications. It's extremely impressive, and I'm extremely proud that the research community is able to do that. The overall budget is around 8 million euro. Now, so what I'll do, I'm not going to go through the 100 and plus research projects that we carried out in 2024, but I'll just show you some examples. One of that is one of the many tests that were carried out in the lab. And I have an interesting anecdote to tell you about this. So there was a visiting scholar, visiting academic from the US that when he entered the lab and saw this thing we were building, he said, "This is absolutely amazing. We would love to have a bell tower like this in our town. You actually build it in the lab to test it, damage, study it." And I agree fully. It is quite impressive. This was, by the way, a project carried out in partnership with ISAC that developed these active mass dampers that were tested in this bell tower. And you can see when you see control off, control on, it means that these active mass dampers are either disabled or enabled in the different tests. You saw some shaking there, perhaps you didn't see it quite well, but you will see better in the next slide where we focus on the top part of the bell tower, and you clearly see the shaking, especially on the left where the device is not turned on. It was quite a spectacular test to see a masonry bell tower built in the lab on the shake table and being tested. But we did not just carry out tests in the lab. We also carried out this extremely large shake table, let me call it, shake table test on site. So what you're seeing here is one of the buildings that was built within the framework of the CASE project, the CASE project after the L'Aquila earthquake. And what we did here, it's my Director General misbehaving. What we see here is we've managed, again, thanks to the ingenuity of those that work here in Pavia, to actually transform that isolated building in a real-life, real-scale shake table to test, to check the way the isolators were still performing 15 years after their initial construction. It's a unique test around the world because in the beginning, as you saw, we were simulating an actual earthquake record. Then we simulated this cyclic testing. This is unique, and it also, you'll be reassured to know, it also demonstrated that the isolating system 15 years down the line was still working perfectly. By the way, in parallel to this test on this building, the Eucentre actually carried out a check of the 7,000 plus isolators installed in those buildings in L'Aquila and produce a report on those that perhaps require some attention with respect to others. Very, very small number. But as I was saying earlier, the highlight of the year had to be the World Conference that was organized in Milan. And Eucentre played a very active role in this event. And again, just some numbers on which we're very proud of. It was the largest ever conference on earthquake engineering in terms of attendance. So 4,250 participants from really around the world. And another interesting point that you see there, right on the first line, you see that out of those 4,200 participants, only 3,000 delivered presentations. So this means that you had 1,200 individuals that went to the conference to listen to others, to interact with others. So it was not just an event where you would go because you want to publish a paper in a conference and you want to present. You went there also to listen and to interact. And this means mission accomplished as far as organizers are concerned. It was a huge success from all points of view, including the fact that, as you can see there, we had 160, well, it was actually 161. I just thought 160 was a nicer number. Technical sessions proposed by the community. So the program was defined by the community, not by the organizing committee. And the exhibition booths, 110, this looked more like a technical fair as opposed to a conference. Quite a successful event. I'll just show you some pictures. This was at the welcome reception. It was too successful, as some of you that were there will know. We ran out of food. There were many more people than normally used to go to these welcome receptions, and this was, we paid the price of the success. In the opening ceremony, you had 3,500 people sitting in that room. Opening reception, which was also quite spectacular in a way when there was a live performance singing an anthem of the conference, led by, the creation of which led by Professor Calvi. We've introduced also this novelty, which cost me thousands of emails up to the conference to explain what it meant, these monitor sessions. Again, we were victims of our success. So the idea was not to have posters, static posters, but to have monitors and allow individuals to do the presentation as if they were on stage, but in front of a monitor. Again, it was very successful, so it was very noisy, and the acoustics were not good. So another negative consequence of a positive outcome. But we also allowed participants to follow tests in the lab. This is a new center, and so we brought a number of conference participants to Eucentre to follow a test in the lab, a collapse test of a gable, of a masonry gable. And for those that did not have the chance to come to this test, they also had, however, the chance to experiment the simulator. So 1,300 people experienced the shaking of an earthquake. But it was not just a question of experience the shaking, so you would go through 3 different runs. One where you would feel the shaking at the ground, another one, the same shaking, but the response at the 5th floor of the building, and then a third run where you would imagine the building seismically isolated. So it was not just go there for the fun of the ride, but actually understand the differences in shaking in such different contexts. The Turandot alla Scala, 1,800 people, participants were there. Very, very special event. Very, very special event. And of course, a big party as well. Not the traditional gala dinner, we went for the party instead. Organized a table football tournament, and here things went a little bit pear-shaped because a team from Eucentre won the tournament. And so obviously rumors were that the tournament was fixed. It was not. It was that the Eucentre team trained a lot, perhaps too much. They did win the tournament. And finally, and this will be also a lead way for Professor Monteiro to now join the stage, the ROSE School party. So there was this ROSE School gathering during the week of the conference. These gatherings, they happen every time we have a world conference. The problem is that we are running out of space. The community is growing and growing and growing. It's becoming more and more difficult to find a place for us to all get together. But it's something really, really special. As was already stated, both this morning and yesterday, by students and current students just graduated. There is the spirit, the community that is created through the ROSE School experience is something special, and you can really feel those vibes in these events. By the way, this photo was taken by Professor Paolo Riva, and who's very tall and managed to take this photo. I don't know how we're going to manage in 4 years' time or 3 years' time at the next conference. I'll leave you with this, with this photo of the ROSE School gathering during the conference, and I'll pass the floor to Professor Monteiro. Thank you.
Thank you, Rui. So yes, we are back to the core of our activities, the students, right? The graduate students. Before going to the graduation ceremony that we been holding in a symbolic manner, because no diplomas are actually handed, I usually spend a few minutes telling something about what's been going on in the past year in terms of ROSE activities. Well, for a program that, I always say the same thing, for a program that has been running for 24 years, it's a hard task, okay, to come up with something new. So I'm just going to provide you with some highlights that do little more than just confirm the success of the ROSE program over the years. In terms of master program, Master of Science level of training, I just want to remind you of our 2-year program that is jointly awarded by the University of Pavia and IUSS Pavia. Applications are still open at the very last, let's say, time frame, and period that you can still apply, and scholarships for next year are still available. In terms of master training, there are news. There are things that might be happening, hopefully, very soon. First thing is we're bringing back the advanced post-Master of Science master program with a reduced duration, in this case 1 year. It is strongly research or practice oriented, so it's not a Master of Science that remains the previous program that I've just illustrated. And it's again jointly awarded, or will be a jointly awarded degree with the University of Pavia and the IUSS, but with a strong model that is, or a strong, let's say, role of the Eucentre Foundation that follows a model that is very common in other universities and other contexts around the world. We have 2 universities that take care of the course delivery, take care of the degree awarding, but we have an interface foundation that represents a connection with engineering practice, with the industry, with the private partners that is very much involved in the program, the same way that also the GEM Foundation in Pavia is involved. There will be 12 courses plus an internship, short duration internship, so it's a 1-year concentrated master duration that will be targeting, very likely, a different audience in terms of candidates or students, and that is fully in intersection with the Master of Science and with the PhD program. So it's a way of optimizing the very high quality academic offer that we have in Pavia in terms of courses at different levels of training. But there's more. So we're also working on the preparation of application for funding of a new master program, also a 1-year program that is very much related to the topics that have been described and presented earlier on by Professor Marini. So we want seismic risk to go hand in hand with sustainability and disaster risk reduction related to natural hazards. The title in green is very much preliminary, temporary, is to be confirmed. So it is supposed to be a program that has a set of vertical courses or courses in series that you can see there in the top row that cover different types of hazards and different also additional complementary interdisciplinary topics. The targets that you see on the right hand of the slide are varied. You have insurance companies, you have banks, you have private, public sector. So all the stakeholders that, let's say, benefit from an increased awareness and increased knowledge with solid research background in risk. So far we have 2 confirmed partners in addition to IUSS Pavia, University of Aveiro in Portugal, and the National Technical University of Athens in Greece. It is going to have also a slightly different structure that allows us to exchange teaching and training capabilities between the partners. So the courses would take place only in 2 partners every year that rotate, so that the lecturers from each partner can go and teach in another country the year after, which optimizes and exploits as much as possible the local capabilities of the different partners. When it comes to the PhD level of training, applications are also still currently open. The deadline is June 16. We have 8 PhD scholarships, so 8 new students that will join a current mass of around 30 students, which is quite an important number, which is also reflected in the 11 graduates that we will list in a few minutes. Some numbers, some statistics on what has been going on at the PhD level. So here you can see the number of applications to the ROSE doctoral program since 2010. There seems to be a cyclic nature of the application numbers, right? We haven't understood yet if there is any logic to this or not, but there appears to be something happening. What I want to highlight, though, is that the number, although of course with natural fluctuation over the years, has been remaining steady in terms of a guaranteed number of applications, despite the challenges that the academic sector faces nowadays and research, with so many opportunities in the industry and in the private world. Another highlight is with these red numbers, you see the number of Italian applicants to the program, which is extremely low when compared to the total number of applicants. It is good because it guarantees an international breadth to the program. As we saw yesterday, 7 presentations coming from all non-Italian students, but it also guarantees, in any case, as natural it is, the presence of the hosting country in the program. If we add the numbers of students that studied in Pavia before enrolling with the PhD program, they increase with respect to the Italian candidates because naturally some of the master students come from outside Italy, but still the international reach of the PhD program is in my opinion, incredible and very much demonstrated. In terms of training, we keep proposing new courses that try to keep up with the new and current demands of the sector, of all the types of communities, relying on the capabilities of the very competent young researchers that we have here in Pavia, and many more that I cannot include in these slides. Including, again, integrated assessment and retrofitting of existing buildings to, one more time, recall the very nice keynote lecture. Finally, just another aspect, we have introduced a new section within the ROSE PhD website that foresees testimonials of ROSE success stories. So we try to ask our ROSE alumni to be as ambassadors as possible of our program. We've seen in the morning how this model works and how this makes sense. So far, up to the graduates in 2010, up to 2010, you can see names like Helen Crowley, we have João Almeida, Ana Beatriz, Didier, Damien Grant, and others that are going to slowly, bit by bit, be added to this page. Some of you in the audience are going to be contacted hopefully soon. So remember to collaborate with us and give us your testimonial. And that's it. So we're now ready for the graduation, to call the students one by one, to shake hands and greet some of the representatives of the institution. So I will ask Professor Pinho, Professor Michele Calvi to come upstairs, who was always the mind behind what is ROSE nowadays and has always been, and Professor Alessandra Marini as the guest this afternoon of honor, and Professor Magenes representing the University of Pavia, if he can also come and join us. Now, you've seen this map illustrated in past presentations. The map was different, so GEM has now produced very recently an updated map of the global seismic hazard model, and we've decided to reproduce it, this overlapping of the country of origin of the 15 graduates that we are going to call in a few seconds, just to show how incredible it is to see how these countries follow the level of seismic hazard all around the world. So the program is capable of sending the message to where it is supposed to. So this is very nice to see. So let's start with the PhD graduates, all the students that finished their presentations and their exams yesterday. Savinos Aristidou from Cyprus. Pablo Garcia de Quevedo, Mexico. Ignacio Agustin Gatti, he's not present. Carlos Fernando Grajales Ortiz from Colombia. Venetia Kokaraki from Greece. I don't know if Venetia is around. I think so. Maitri from Sri Lanka. Carlos Mesta Cornetero from Peru. Kenneth Emilio Tarola Madrigal, Costa Rica. Naveen Raghuralaniman, India. Serena Sapio from Italy. And Lana Todorovic, Montenegro. Then we had 4 master's students graduating over the past year. Shubhan Falah, Iran. Tomás Mejía Saldarriaga, Colombia. Daniel Vargas Picardo, I don't think he's present. And finally, Elias Yacoub from Syria. Elias? No. And this is all for this year. I'll see you all next year, I guess.